of chain letter reserve estimate. First, we will briefly introduce the chain letter method, and then we'll introduce the author of this paper. We'll talk about his method and then give a numerical example. So let's start with the introduction. Chain letter method is also called loss development method. Since it's widely used and simple, chain letter method is one of the most popular methods for estimating reserves. Chain letter method seems to have no assumptions and leave the impression of simplicity. However, this impression was wrong, and we'll talk about this later. This method is based on incremental or cumulative paid or reported triangles. By calculating the age-to-age vectors for the reported or paid loss triangle for each development year, we can obtain cumulative loss development factors, which we use to project ultimate loss. Next, we'll talk about the author.
The author of this paper is Thomas Mack. I'm going to introduce him briefly. He worked as chief actuary in Munich Reinsurance for 30 years and retired in 2006. He is a member of German Actuarial Association and also an honorary member of many actuarial institutions. And he published several useful papers and was awarded the joint second, third prize in the paper competition. Here, let's talk about the wrong impression of chain letter method. Most people consider this method is simplicity because of it is distribution-free and based on almost no assumption. But in this paper, the author clarified the wrong impression of the method. Let's see how did the author clarify the wrong impression. The chain letter algorithm has some far-reaching implication. This implication allowed to measure the variability of chain letter reserve estimate. With the help of the measure, it's possible to construct a confidence interval for estimate client amount and reserve. And such confidence interval can help practitioners consider business strategy. And also, confidence interval also distinguish difference between the chain letter method and other method is significant or not. And I'd like to hand the presentation over to the next speaker.
Thomas' method has 3 steps. Check the assumptions, calculate the standard errors, and establish a confidence interval. Let's see how he derived and used. There are 3 assumptions he found in chain letter method: expectation, independence, and variance. Calendar year effects is the main reason for violating the independence assumption. When DJ is larger than usual, AJ-1 is larger than usual, and AJ is smaller than usual, then there is a calendar year influence. We order for every K, and if Fk is larger than median, it is in set L. If Fk is smaller than median, it is in set S. When Cj is significantly smaller than Lj plus Sj divided by 2, then there is some reason for a specific calendar year effect. In order to design a formal test, Thomas assigned n equal Lj plus Sj and m equal n minus 1 divided by 2, and we can calculate the expectation and variance of Cj. Because Cj are almost uncorrelated, we can add them together and assume that Z approximately has a normal distribution. Thus, when Z falls within the range, there is no significant calendar year effect. The expectation assumption can be interpreted as an ordinary regression model, yi equals C plus xib plus error. Expectation of error is 0, and in this special case, C equals 0, B equals Fk. Then use the usual least squares method, minimize this formula to get Fk0. Rewrite Fk0, and Thomas found that this is a CIK square weighted average of individual development vectors, which implies that the variance is the same for all observations. This is not in agreement with the variance assumption of chain letter method. In order to be in agreement with the variance assumption, we should use the weighted least squares method. When Wi equal 1 over Cik, we get Fk1, and when Wi equal 1 over Cik squared, we get Fk2. After transforming the estimation of the H2H factors into the regression framework, we are now available to check the expectation and variance assumption by plots. Use the plot Cik plus 1 against Cik to check if linearity is acceptable, and use plots 0, 1, and 2 to find out which one shows the most random behavior. The second thing we want to know is the average distance between the forecast CII and the future realization CII, which is mean square error. The mean square error is on the condition of knowing all data observed so far, because we want to know the error due to future randomness only. Since the mean square error depends on the unknown model parameters, we must develop an estimator, and the square root of the estimator is standard error. From the equality of the mean square error, we can know that standard error of Ri equals standard error of Cii, and Thomas also derived this resulting formula to calculate the standard error. Third step is to establish a confidence interval. From the equation Cii equals Cii plus 1 minus I plus Ri, we can know that the probability distribution function of Cii is completely determined by that of Ri. Thomas found that normal distribution may not be a good approximation of Ri because the distribution of Ri is skewed, and especially when standard error of Ri larger than 50% of Ri, the lower limit becomes negative. Thus, Thomas used an approach based on the log normal distribution to calculate the mean and variance, and shift the confidence interval to Cii. Next is the example.
Okay. Thank you. Now we'll give a numerical example of this research. The first table is the loss development of a general liability automated facultative segment, and by using the formula that Cindy mentioned before, we can compute the H2H factor and FK0 to FK2 by using FK0 to FK2, we are able to project the loss to the automate, which is 120 mouth in this case. Next, we can plot the regression Ci2 against Ci1 and residual for Fk0. We can have 4 observations from these plots. First of all, the regression line does not capture the direction of the data points really well. Secondly, if Ci1 is smaller than 2000, Ci2 will be underestimated. And if Ci1 is larger than 4000, Ci2 will be overestimated. Thirdly, from the table below, when I equal to 10, Ci10 is 2063. C102 is within the block of data plotted. Lastly, those two figures show any forecast of C102 is associated with high uncertainty. If in the future we have Ci1 outside of the interval of 2000 and 4000, it would be appropriate to add another parameter by fitting a regression line. Those are the regression plots from Ci4 against Ci3 and Ci6 against Ci5. We can find out that those two regressions are curvature and might due to insufficient data, and we can hope that two curvature offset each other. For those three regressions, the plots are quite satisfactory. The trend in the residual for k equal to 7 and 8 have no significance because of a few data points. Next, we can calculate the standard error. In order to estimate standard error, we need to estimate alpha k squared first. This plot shows that long alpha k squared and k seems to have linear relationship, which can be used to estimate alpha 9 squared. We then obtain alpha 9 squared as 1.34. From the previous steps, we are already able to project losses to the future, and now we can also calculate Ri by calculating the difference between Ci10 and the respective element of the main diagonal. For I equal to 2, 3, and 10, the percentage of the standard error is more than 100% of the estimate reserve. When I equal to 2 and 3, it will not cause concerns since the amount of reserve is small. But if I equal to 10, it will cause a bigger concern. Since it's the latest year, we are unable to precisely estimate the loss. Next is obtaining confidence interval. Since all standard error is nearly 50%, we use log normal distribution in all year to compute confidence interval. There are 4 steps. Firstly, compute sigma I square, and then compute the overall upper bound. Since each level of confidence corresponds to a certain percentile t of the standard normal distribution, we can use the solver function in Excel and get t equal to 1.13. Lastly, we need to repeat step 2 and step 3 to compute the lower bound and obtain the corresponding t equal to negative 0.2. This means that 66% of confidence interval for each accident years leads to a 80% confidence interval for the overall reserve amount. We can finally get the confidence interval for 80% probability overall and the empirical limits. The empirical limits contains the minima and maxima size of the ultimate claim amount. Each H to H factors is replaced with the minima or maxima individual development factor. For I smaller than 4, the confidence range of empirical limits are smaller, and the range becomes larger as I increase. And this approach does not seem reasonable. Also, in this example, we use log normal to compute the confidence interval. If we use normal distribution, the allocating to the accident year would be different. Finally, here's the conclusion of this research. Firstly, the author developed a rather complete method on the basis of a simple chain letter method. Secondly, few observations form an uncertain basis for the projection to the ultimate. Thirdly, the statistical instruments developed do not reject the applicability of the chain letter method, but the result must be judged by an actuary. Next, the unexpected future change can make all estimates obsolete, but for many normal cases, it's good to have a simple and easy explained method. Lastly, there are invaluable advantages of simple model over more sophisticated ones. Thank you for listening.